Well, our next speaker is Ihechukwu Chinyere from the University of Essex, who will be talking about hyperbolic groups of Fibonacci type.
Okay, thanks, Alan, and thanks to the organizers for inviting me. I was here a bit earlier, met Suraj. I don't think he's still here. Okay, so anyway, yeah. So today I'm going to tell you about hyperbolic groups of Fibonacci type. First of all, I'll tell you what these groups are, and of course the what we did and what is left. So a fixed set X, and f of X is the free group with X as basis. If you take a word W in your free group, you can define a presentation of this form. So it has n generators and n relators, where each relator is obtained from W by applying this automorphism of the free group. So just shift the subscripts of the generators appearing in W by 1 in this case, and up to n-1 when you do it the next time you come back to W. So this is what is called a cyclic presentation. You can think of the free abelian group of rank 2, which 2 generators which commute. So this has a cyclic presentation of this form. Okay, so you can notice that this is redundant. We don't really need this relator to get this as a presentation of this group. But anyway, that's an example of a cyclic presentation. So a group is said to be cyclically presented if it has a presentation of that form. Okay, so we usually denote it by that. Some examples are cyclic groups. Cyclic groups are examples. Free abelian group, we just saw one. Free groups and Higman group and many others. Okay, so but the groups that I'm interested in today are these cyclically presented groups of this form. Remember that this is the W now, so this means that it has n generators x0 to xn-1, and the relators are just shifting the subscripts of this this particular W here. M and K are integers, so integers less than n. Okay? Less than or equal, less than n, from 0 to n-1. So these groups were introduced independently by Johnson and Modestly and this group of authors for algebraic and topological reasons. In general, cyclically presented groups have been studied from this perspective as well. They have very close connection to the topology of three-dimensional manifolds. So, yeah. Anyway, so this was introduced as some generalization of Fibonacci groups that was introduced by John Conway. So when you take M to be 1 and K to be 2, you get the Fibonacci groups. And there's the Siratsky groups, which is when you have M to be 2 and K to be 1. And also the Gilbert-Howie groups. This is the case where K is 1. Okay, these are some subfamilies that have been, very well studied. Okay, so the task today is to try to classify the hyperbolic groups in this family. Okay, and so I'm going to define what I mean by, of course, everybody knows, but just to revise what we mean by hyperbolic groups, I'm going to use Van Kampen diagrams to do that. So if you have a group with a finite presentation, a word in the group, a word in the generators of the group is trivial in the group if you can write it in this form. This is the same thing as saying that there is a reduced Van Kampen diagram which has the W as the label of the boundary. Okay, so this the smallest alpha for which you can express W in this form is called the area of the W. And you have the n function, which is a map which takes, so if you have a word which is trivial of length at most m, so you look at the, the smallest alpha in the previous slide, for which you can express W as as that product, and then you take the maximum of all this. That's just the image of the then function. And you say a group is hyperbolic if it's got a linear then function. Okay, so that's one way to define hyperbolic groups. Examples are finite groups, free groups, but groups which contain free abelian group of rank at least 2 is not hyperbolic. Okay, so yeah, so we want to so the plan is to use the Van Kampen diagram somehow to be able to decide if these groups are hyperbolic or not. Okay. Any questions so far? Okay, so I'll just continue. So again, the question we want to answer is which groups in this family are hyperbolic. So let me tell you about the Fibonacci groups. This has been done. We know that Fibonacci groups are hyperbolic except when n is equal to 6. Well, the even case was done a long time ago. Well, not so long, but anyway, 1998. But the odd case was just done this year. It's been open for a while. It was just done earlier this year by Chalk. So this is for odd cases greater than 9. These are the even cases. Okay, most of the lower values are finite, so they are hyperbolic. The case 9 was done computationally, so it was a difficult problem at the time. People didn't even know whether this group was hyperbolic, whether this group was infinite or not. It took some computations to be able to do this. Okay, so that's the Fibonacci groups. There's Cebulski groups as well. These are not hyperbolic. Oh, I made a mistake, sorry. So this is supposed to read not hyperbolic for n greater than or equal to 6. So these ones are finite. Again, the way to show this was to show that the group is the fundamental group of hyperbolic manifold. And that follows that the group is hyperbolic. Okay, the Gilbert-Howie groups are hyperbolic except when n is 7. Again, computationally. These cases were done computationally. These are finite and well, most of the results were proved here, except in these 2 cases, which was covered here. And then a recent result of myself and Williams, we showed that this class of Gilbert-Howie groups are not hyperbolic. So the whole family here is not hyperbolic. Okay, so today I'm actually going to tell you about this particular result. So the idea is to go into the proof. So it turned out that to somehow almost classify all the hyperbolic groups in this family, this was the missing result, which we proved sometime last year. So I'm fixing a p which is in this range. And I'm taking n to be greater than 7p. Again, this condition is just so we can use Van Kampen diagrams to do this. What you can show is that the group is hyperbolic if this condition is satisfied. Okay, so the previous slide was for T6 groups, and this actually covered the T5 groups and the remaining cases. Okay, so right, so now we have a theorem. So if you combine all the results that I mentioned before, you get this theorem. Okay, so I'm setting n to be at least 13 here because actually it's so I want to write the result in terms of A and B, and if I can only do this if I set n to equal to greater than or equal to 13 For lower values, it doesn't really fit into this picture nicely. So for today, let's assume that n is greater than or equal to 13. Most of the lower cases are actually finite groups, and there are a few which are not hyperbolic. Okay. So the Fibonacci groups fall into this class. The Zariski groups, remember, the Zariski groups were the cases where k was 2, I think m was 2 and k was 1. And if you put it here, you're going to get this. So k is 2 and m is 1. So this will be 1 and this will be 1. Sorry, is that correct? So Zariski groups were the groups that x0, x2, x1 inverse. Okay, so this corresponds to m equal to 2 and k1. So m is 2, k is 1, and this is 1. So this will give you -1. So a plus b equal to 0. So yeah, this fall into this class. And Fibonacci groups, if you check, will fall into this class. Okay, so this is the result. So the last theorem I mentioned here was the only ingredient left to get this classification. So what I'm going to tell you now is the ideas that go into this proof. Okay, so the way we do this is to show that the function is linear, and we're using something called ant-lane argument. So if you have done something in equations over groups, you would have heard of the Ihechukwu car crash theorem. So he used this idea to prove that certain types of equations over torsion-free groups have a solution. So yeah, so that was the motivation for defining for the name that we've called this. Okay, we'll get to that. So this is the idea. We're gonna have a Van Kampen diagram, and we're going to use the Van Kampen diagram to show that the then function, this group is linear. Okay, so this is the setup. Again, we're going to work. So D is going to be a Van Kampen diagram, a reduced Van Kampen diagram. Somehow we're going to assign curvatures to the corners of this Van Kampen diagram. So I'm not sure. So if you have a Van Kampen diagram, this is divided into vertices and faces. Okay, so if you have a vertex here, this is what I'm calling corner. These are corners. And the vertices here are called boundary vertices. And any vertex which is not on the boundaries is an interior vertex. Okay, and these are called faces. These are called the boundary vertices, and these are the interior vertices. Okay. Okay, so you assign angles to these corners in this way. And then we can use Gauss-Bonnet theorem, for example, to show that the sum of the curvatures has to be 2 pi, because the Van Kampen diagram is planar, it's a topological disk. So the Gauss-Bonnet tells you that the sum of the curvatures has to be 2 pi. Yes, somehow you use the Gauss-Bonnet curvature, Gauss-Bonnet theorem to show that it's enough to prove this result here. Okay, so if you can show that the curvatures of the vertices is less than 0, interior vertices, less than or equal to 0, and the sum of the curvatures of the faces is minus number of faces, then G has a linear then function. So it's not very hard to do this. Okay, just follow from the Gauss-Bonnet theorem. Okay, so this is our target. Our target is to achieve this. Now we're going to assign a curvature to the corners so that this condition holds. So we just have to prove this. Okay, so because the the relators all have length 3. The faces of a Van Kampen diagram are going to be triangles. And so this comes from the relators. And you can see that the triangle's got different kinds of corners. So there's a corner with X, which is neither a sink nor source. There's a corner labeled Y, which is a sink, and this is labeled Z. Okay. Because the Van Kampen diagram is assumed to be reduced, you can show, for example, that you can have labels like this. A label is if you take an interior vertex and you look at the labels around it, so what the corners are, and you read that as a word in X, Y, and Z, that's what we call the label. You can show that this can never happen because the diagram is reduced. Okay, so let us assign angles in this way. So if you have a vertex of degree Q, which is an interior vertex, you assign angles 360/Q to the corners. Okay, this will give you that the curvature of the vertices will be 0. Okay, but on the boundary vertices, I want to assign 29. Okay, just for 29 works here. You can assign any angle that you want. Okay, so with this assignment, the vertices, interior vertices, all have a curvature of 0. So we have satisfied the first condition there. Now we have to worry about the faces. Okay, so I'm going to define 2 kinds of faces, the black and white. Black faces are those containing a vertex of degree less than 8, and the rest are white. Okay, so if you have a white face, are those faces that contain a vertex of degree less than 8. Okay. Let me say that again. Black faces are those containing a vertex of degree less than 8. The rest are white faces. So if you have a white face in the Van Kampen diagram, then the curvature, remember the curvature is defined by -180 plus, sum of angles in that corners in that face. And if you do that, you get -45. Okay, so this really have very low curvature. But these are fine. Remember, we want to achieve this here. This is all we want to achieve. So the white faces give us really negative curvatures. The problem is the black faces. If we had the black faces negative curvature, then it would be fine, but that's not the case. So here's a lemma that is very useful. Remember, we had this P, which is 3, 4, 5, and we can show that if V is a vertex of degree less than 8, then the label of that vertex will have to be a Z to the power something. So it's Z3, meaning that, let me see if I can. So meaning that if you look at interior vertex of degree, so when P is 3, you're going to see something like that. Okay, that's what I mean by that, and so on. Or P is 4 and you have that, or P is 5. So these are the only ways you can have a vertex of degree less than 8. So that degree 3 or 6 in this case, or degree 4 or degree 5. But we can show, for example, that something like this cannot happen in the Van Kampen diagram. You can have this. If you have this, you're going to have either XX here. So because we said we can't have XS or something else. So those things will happen if you have a face like this. So this can't happen. You can't have this in your Van Kampen diagram. You can have a black face. Remember this, you can have 2 black faces joined in this way. Okay, so because you can have that, you can have all this as well in the Van Kampen diagram. Okay. Let me try to explain why. So if you have this in the Van Kampen diagram, remember this is a black, so this is a black face, means that there is a corner which is labeled Z. Okay, I told you. And you can show that it has to be this corner here, okay, this particular corner. You can show that this has to be the corner here, and this has to be the corner here. And we showed in the last slide that we can have something like, you can have a Z here and a Z here. So since this is a Z, this cannot be a Z. This is a Z, this cannot be a Z. and this is a Z, this cannot be a Z. So you've got a face in the Van Kampen diagram. None of the corners can be labeled by Z. But every face in the Van Kampen diagram has to look like, it has to be X here. Somewhere has to be X, the other has to be Y and Z. So you have to have the corner labeled by Z. But if this happens, then you have a corner which cannot be labeled by Z. So these are impossible. The same argument shows that all these are impossible. Okay, these are the impossible configurations, some of them. Okay. Okay, so let me just recall what we've done so far. We want to show that this condition holds, and we are assigning these angles to each corner of a vertex of degree Q, and then the curvature of any three vertices at least 0. It remains to show this, and the curvature of a face, which is white, is at most minus 45, and the highest curvature of a black face, you can show that is at most 30. And the aim is now to show that the average curvature has to be at -1, which is what we want here. Okay. Okay, so now we do this with so I'll now tell you how to do this. So in some sense, all we need to do is to kind of show that the average curvature, okay. That's the difficult thing, is to kind of show that the average curvature is at most minus the number of faces. Okay. But it's not clear how to do that. It's not. So this is why we call this, introduce this antling argument. Okay, it's some way of averaging this curvature. Okay, so because I'm going to explain to you what this is. So consider an ant taking a walk on the Van Kampen diagram and obeying these rules. So the ant has to begin somewhere called home. It's going to be a black face. It begins from home, and it walks into it never walks into a black face and never crosses a boundary. So the boundary of Van Kampen diagram, the ant is not allowed to cross the boundary, which is kind of natural. But if the black face is adjacent to a white face, then the ant must walk into that white face. Okay? It must move out of a white face into an adjacent white face if the white face is adjacent to a black face, which is different from home. Okay, I'm gonna explain this with an example, and it's not allowed to backtrack. Okay, let me just make these definitions, then I can give you an example. Okay, so an ant walk is a set of the white faces in the path of an ant following the rules that I just mentioned. And an ant lane is this ant walk together with the black faces that are adjacent to it. So we put this notation. So the ant lane is said to be of type BW if that ant lane contains B black faces and W white faces. Okay, and a white face of an ant is called a junction if it's not adjacent to any black face, and an ant lane is maximal if it's not properly contained in another ant lane. Okay, let me give you an example just to so this is the piece of your Van Kampen diagram. So I've labeled the B's being the black faces and the W's are for white faces. Okay, the ants are placed in all the black faces, and they begin their journey from there. So imagine an ant which is placed here. Okay, if you have an ant here, Alan, please tell me when it's like 5 minutes or so. Okay.
I think you're probably 2 minutes or so.
Okay, let's hope I can explain this before. So the ant begins its journey here. Okay, I'm going to draw so a black face, and it walks into this white face. So now it's supposed to leave this white face to another white face, but it can only leave this white face if this white face is adjacent to another black face, which is different from this. So which is the case here. So it goes into this white face. Now it has to leave this white face to another white face if this is adjacent to a black face different from that, but there's no other black face different from that, so it stops here. Okay, so an ant begins here, goes into this white face, and this white face is not adjacent to any black face, so the ant will stop here. So it's and so on, you know. So this first part I've called that's the L1, so it means B naught. This is just the L1 that I just described here. It's of type 2, 2, so 2 black faces and 2 white faces. And if you do the same for L prime, if it begins a journey here, it's gonna finish here. Okay, I think it's gonna finish somewhere here. Okay, here to there, there's a black face there, there's a black face there. So both of them meet here. So this is what I've called junction in the previous in the definitions. Okay, so what we are going to do is that we have these two band planes, and we're going to glue them together where we don't want intersections. So this is maxima, this was maxima, this one here wasn't maxima, it was contained in this. So we're going to take the set of these maxima and planes and we glue them along the junction. So these two are maxima, I've glued them to get that. This one is now of type 5-4, okay? And what you can show is that you can now look at the Van Kampen diagram there, and you take L, which is the set of the maxima and planes, and they join. So that operation is called join. So you're gluing two if they intersect. So this set, nothing intersects in this set now. And you can show that there is no intersection. But now you can now calculate the curvature of this, the average, the curvature of this is the, curvature of the faces divided by the number of faces. And you can show that this is at less than or equal to -1. So this is just the trick to get us to get this summation. Now you can complete the proof. We want to show that this thing here is less than or equal to -f. And then this thing here is just the sum over the things in L and the things not in L. The things not in L are the white faces, so the curvature is at most 45, and the things here, we have shown that the curvature is at most -1, and overall this is less than -1 of f, and that's that. Okay, so that's it. That's the whole idea of the paper. I'll just leave you. So we understand the curvature, we understand the hyperbolicity status of all the groups in that family, except for these two groups. Okay, so if you can handle these problems, in fact, these groups, we don't even know if they are finite. We don't know much about them. We don't even know if they are, I think we don't know if they are three-manifold groups as well. We don't know if they are finite. We don't know if they are hyperbolic. So if you can do any of that, it will be nice. Okay, I think that's it. Thank you very much.
Okay, great, thank you. And does anyone have any questions? Oh, we should sign the speaker. All right, thank you very much for your talk. Questions? Does anyone have any questions? Well, I have one related to the previous talk. So it seems to make sense, the definition of the definition you gave of a cyclically presented group really works for any automorphism of the free group. So have people thought about these more general groups?
So that's for me.
Yeah, sorry.
I don't know if so I don't see the connection between.
So the connection was so in my mind, if you've got a periodic automorphism, the one that's finite order in the outer automorphism group, then it's guaranteed to be finitely presented because you're finite. You start repeating up to conjugacy, and you don't care about that. You just start removing them.
But so that's right. So right. Yeah, but it's not a cyclically presented groups. The whole thing is not, is it?
I mean, the definition makes sense because you're just taking a word and then applying an automorphism to it, and so on.
Yeah, but this is specific automorphism. Is the shift automorphism? It's not any kind of automorphism.
Yeah. So, but I was just wondering if you know if anyone's ever thought about such a question, such a generalization.
I think people have. I think people have considered some other kinds of automorphisms, like instead of acting by the symmetry, by the cyclic group, this is a cyclic action, you can act by any kind of maybe the symmetry group or something else. I think some people have done a few things about that, but in order to be able to prove results, might be I think that's why people it's a lot easier to work with cyclic groups.
Yeah.
The extension is quite nice. It's a 2-generated group. Yeah, semi-direct product. Yeah.
Okay, great. Well, we should thank Ihechukwu.
Yeah.
Apologies again.
Thank you.